So in the last lecture, we discussed about Bayesian method, and we said Bayesian method provides a powerful tool that can basically integrate the data and the knowledge that is coming from engineering judgment or domain knowledge or expert knowledge. So this method is basically can be used with data and domain knowledge. So to illustrate that, we will use here an example, and this example is related to uncertain coin. So you may have come across flip coin examples. So if you toss or if you flip a coin that is fair enough, then there is a probability of getting a head is equals to 50% and probability of getting tail, that is 50%. So those kind of coin is called fair coin or unbiased coin. But in some coin, if I have the probability of getting head and tail is not equal, those kind of coin are called biased coin or unfair coin. So let's say we have a biased coin in this case. So question says, let us consider a bias or a skewed coin for which the probability of getting head is uncertain and P is the probability of getting head, and this is uncertain. This means I don't know what is the value of P. If I have a fair coin, then value is fixed, that is 0.5. But now in this case my coin is unfair and I don't know what is the value of P. It can be anything. It can be 0.3, 0.4, 0.5. So let's assume P is a random variable. So this is a random variable which can take different value. It can take a value of P1, it can take a value of P2, it can take a value of P3. So I don't know what is the value of P. So let's take P1, P2, P3. These are the values that P can take. So I can say P is a random variable that can take value of P1, P2 and P3. Other values are also possible. In this case we are only considering 3 values. So we are saying the random variable P can take discrete values. P1 is equals to 0.3, P2 is equals to 0.4 and P3 is equals to 0.5. Let us assign a distribution to P. So now we want to assign a prior distribution because P is a random variable, then I can define a distribution. So if you remember, in previous classes we said a random variable can always be defined by a probability mass function. So I will have corresponding to P1, I will have some probability, and on the y-axis we will have probability mass function. Corresponding to P2, I will have some probability, and corresponding to P3, I will have some probability. So for a random variable, we can define a probability mass function. So this is what we are saying. We can assign a distribution to P and we'll call this a prior distribution. Let's say this distribution is shown here, so that the corresponding to P1 0.3 probability mass function value is 0.6, 0.4 corresponding value is 0.2, 0.5 again corresponding value is 0.2. So if you add all this value, that is 0.6 plus 0.2 plus 0.2, that is equals to 1. So basically this satisfies the condition of probability mass function, that is sum of the PDFs is equals to 1. So ordinate of PDF. So this is indeed a probability mass function. Now let's say we perform some experiment, and that is we are getting some evidence from the data. So we are doing some experiment and we are basically flipping the coin 5 times, that is 5 coin tosses, and I get 3 times head. Let's denote this as H. So this event of getting 3 head in 5 coin toss is denoted by H. So H is nothing but 3 head in 5 toss. So this event we are denoting by H. Now event H can happen if any of the three values of P bear true. So either it can happen if I have P1, or it can happen either I have P2 or we can have P3. So if any value is true, either P1 is true, P2 is true, P3 is true, I can get a 3 head in 5 tosses, but in all cases we will get different value. We'll understand this soon. So getting 3 head in 5 tosses corresponding to P1, I can use binomial distribution. So using binomial distribution, I can find what is the probability of getting head in 5 tosses, getting 3 head with a probability of P1. So basically we can define 3 scenarios. And this scenario is H can happen if P is equals to P1, that is 0.3. H can happen P is equals to P2, and H can happen when P is equals to P3. So my event H, this event can happen in 3 ways, and these 3 ways are mutually exclusive. So now question is, find the total probability of occurrence of the event PH. So we have to find what is the probability of occurrence of PH. So how we can find this PH? So as I said, this PH can happen in 3 ways. So we can find PH. It can happen when probability is P1, and then we have to find what is the probability of P1 plus given P2, what is the probability of P2 plus PH given P3, and then what is the probability of P3. So this way we can calculate PH. So let's use Excel sheet to calculate this. In this case, this is a simple example, so you can do this numerically also, but it's better to do by Excel sheet so that if you have more number of cases, you can extend the same thing. So we have 5 number of trials, that is 5 coin tosses, and in these 5 coin tosses we have 3 times that we are getting head. Now probability of occurrence like P1, P2, P3, P1 is 0.3, 0.4 and 0.5, and the corresponding probability was 0.6, 0.2, and then so these probability were here, these values are 0.6, 0.2, and then somewhere here, so this value is here 0.6, 0.2 and 0.2. So this value is here, so we have the prior probability, that is 0.6, 0.2 and 0.2. So then we have to find PH. So basically we can find PH using this expression, that is PH P1 times P1, and then I have to sum. So I can simply write sum of PH Pi times P of Pi. So this is nothing but likelihood. So if you see the Bayes theorem, so this is the Bayes theorem you have, and then if you sum all the likelihoods, so this is basically sum of all the likelihoods. Sorry, not the likelihood, but likelihood times prior. So this term is likelihood and this term is prior. So this is basically normalization constant. In this case, this term is normalization constant and this term is likelihood. So this is P of H times Pi. This is likelihood. That is, in this case, we can use binomial theorem. So this is, I have, in this case, P1 is 0.3. So this means I have to get among the 5 toss 3 success, that is 5C3, 0.3 raised to the power 3 and 1 minus 0.3 raised to the power 2, and then similarly I have to sum other terms. Now let us use Excel to calculate this. So this is prior, and then likelihood is nothing but 5C3. So this term is, in Excel we have function binomial distribution. So bino-dist, and then press tab key, and then this asks numbers, trials, and probability and cumulative. So we are looking for 3 numbers, and then trials is 5 and corresponding probability is 0.3, and this is false. So we are looking for PDF, not the cumulative one, and then I can put a $sign here. And then if I drag this, I will get the likelihood corresponding to 0.3, 0.4 and 0.5. Now let us calculate normalization constant. First is likelihood times prior, and this value is prior, and then if I sum, I will get the normalization constant. And this is also the probability of getting head. So this is equals to PH. That is asked in the problem. Now we can also calculate posterior distribution. So if you remember, this term is posterior distribution. So I have this first term, likelihood times prior, divided by the normalization constant. So both we have, this is likelihood times prior, and if we divide by the normalization constant value this, I will get the corresponding posterior. So this is equals to this value and divided by this value. And then let us fix this. So if I drag this, so this will give me corresponding posterior distribution. Now we can plot histogram for prior as well as posterior. So we have already plotted this histogram. So this histogram, this corresponds to prior. So blue corresponds to prior in this case. Now this value is 0.6, 0.2, 0.2. So 0.6, 0.2, 0.2. And this corresponds to posterior. Now this value is 0.4 to 23, and this value is 0.24, and this value is 0.33. So this is about using Excel to calculate prior, to calculate likelihood times prior and posterior distribution, and we can also get total number or total probability of getting an head. So if you see this, this is plotted, same thing is plotted here. So this updating procedures suggest prior confidence about P was 0.3 has been reduced. So P1 value, initial value corresponding to P1 is equals to 0.3, corresponding probability has reduced. So I am having less chance that my coin will show a head with a probability of 0.3 because I have got a head, so my initial probability has reduced and this probability has increased because I have got a head. So another is prior confidence about P is equals to 0.5 has basically this is increased. So this is not reduced, so this is increased. So you see, once we have only one data point, now my prior priority has got reduced as well as some of them has got increased. For example, in this case, if I have got a tail, in that case my priority will look something like this. My final priority, this would have increased. So this value would have increased, and probably this value has got reduced. This we can say because I have got a tail. So this means in that case, that is a hypothetical situation, getting a tail is higher priority. This means getting a head is lesser. So we will have something like this in that case. So we can stop here and then we will discuss one more example in the next class. Thank you.